I start? So, hello everybody. I'm very pleased to see you today, and I will be talking about cellulose flow technology and how we manufacture and design centrifugal pumps. So, my name is Elisa Klock, and I'm the technical director for Clyde Union Pumps, located in Annecy in France.
Good morning. My name is Brian Germain. I'm the Global Engineering Director for Cellulose. Cellulose Flow Technology, a provider of pumps and valves for the nuclear industry. And as Elise said, we're going to talk about safety critical pumps today.
So I will start with a quick presentation about what is a safety circuit. I will be focusing on PWR, so pressurized water reactors, because this is the type of reactor we are providing pumps, and of course it's my competencies today. So for safety circuits, we have three main safety circuits. So the first one is what we call safety injection. Second one is containment spray, and the third one is emergency feed water. So the role of these circuits is to control the reaction within the reactor building, to make sure that the fuel is cooled, and also to keep all contaminated debris within the reactor buildings. So these circuits, they will support these safety parameters. So safety, this is a green circuit here. So here. And the role of this circuit is to inject fresh water, cool water from the water tank in case of an accident. For instance, an accident can be a piping rupture. The second system is a spray pump here in orange. And this circuit will allow to release the pressure within the reactor building in case of an accident, but also as it will be spraying water on the top of the buildings to drop down any debris that are irradiated. And the third circuit, it's in pink here. It will not be on the primary loop. It will be dedicated to the secondary loop. And it's also the same thing. In case of an accident, you can have a piping rupture, for instance, and then you will lose the flow within the secondary loop here. And in that case, the steam generator will be not operating right without any cooling of the primary loop. So we will have a system here that will inject water directly here. For all this circuit, what is very specific is that it will operate in critical condition, because you are in an accident case, and in that case we need a system and a pumping solution that is very reliable, that will work in any case, the one we have forecast, but also potentially the one we have not forecast. So it's a very specific condition of working, because you don't have one single duty, you know we will operate continuously there. No, it's not the case. You don't know what's going to happen, but you know that the pump have to pump, whatever. So when we start discussing safety accident, you can have different type of critical events. So it can be a little bit simple like a seism, or it can be a piping that is burst in the system. It can be a thermal shock. It can be a loss of pressure, or even flooding in some cases, and you lose your electrical supply. You can have very strong environment, like a very high temperature, high humidity, high radiation level, and everything that is constraint and disturbance for the pumping solution. So when you have all these events, solution is centrifugal pumps, because it will help you to provide high pressure on a high flow range. Because as you don't know exactly what will be your duty points, and you have several duty points, you need to have an operating range of your pumps that is very wide. You also have power constraint, because when you are in an accident, all the safety system starts, and all the power supply, the power request is very significant. So you need to make sure that you absorb power is as less as you can. You can also have debris when you are in a very severe accident. And for instance, when the water tank is empty, the safety pumps, they will take water from the containment sump where you have all the leakage with any kind of dust, concrete, paint flakes, whatever you can find on the ground of a reactor buildings. And also, you need to have minimum support system, because the more system you add, the less reliability you will have. So for instance, we will try to remove all heat exchanger. So once we have identified the need, then we will do, the order will come in Celeros Flow Technology, and we will do our own technical risk analysis. So how we can answer correctly to this type of requirement. So we will identify a risk of cavitation on the pump, a loss of suction, so potentially the pump will on-prime, but it has to start all over again. You can have vibration, pressure pulsation, contact between static stator and rotor. You can also have a risk of erosion due to the debris. So against this, we will find a technical solution. So for instance, we'll have a very rigid design on the pump to avoid any type of vibration, pressure pulsation. We have also worked a lot on adding components in our pumps that we call inducers. But we have worked strongly on the capability of these inducers so that we can reach very, very, what we call NPSH, so low NPSH, to increase the power of absorption to have, if we have cavitation within the pump will still manage it and still operate whatever. Of course, we verify our design with calculation, FEA. We will use specific coatings, specific materials to be debris resistant. And also, we will work very, very strongly with our customer on one side and our supplier on the other side. So if I go to the pump, so technical solutions as we provide for safety injection. So these are examples for current PWR. So what is specific on this machine is its flow range. So this pump will be working at its minimum flow, but also on the maximum flow in a case of a rupture. And adding with this, we will lose suction pressure on the pump, and we have cavitation. So that's why we have developed, we've done tremendous analysis on this, on this type of equipment here. And so that today, we can reach suction-specific speed up to 800, so something like 40,000 in US units, which is about 4 times what you can normally do in oil and gas industry. We also have a design that complies with high temperature, like 180 degrees C today, without heat exchanger on the mechanical seals. So we have developed with our supplier new equipment. And also, we've done additional development to reduce the number of weldings, because welding today is a very critical activity, and we have to make sure that we comply with it. And the best way to comply with welding requirements is to have no weldings. So this is what we do now. Spray pump. So the spray pump is a pump that we call the sprinkler. It's the one that is on the top of the reactor buildings. So just to show you quickly the evolution through the age. So back in the 80s, we had a vertical pump, quite simple, double suction. But over the years, the requirement has changed, and the requirement on suction pressure being very low has forced us to go to add an inducer in our pump, and also to increase the number of stages. Today, the design has changed again. So we are back to a single stage pump, but with very significant requirements on NPSH, so very high cavitation level on it. So we had to put an inducer, but as we wanted to be very compact, to use less space as possible, we have increased the rotation of the speed. And the only way to have a high rotational speed on a pump and no cavitation, today the solution we have found is these inducers that we have developed internally. And the last system, it's emergency and auxiliary feed water. So these ones are on the secondary loop. So you will not have any radiation requirement on this type of machine. It's only on safety injection and spray pumps. So this one, I would say, are a little bit easier to design because you have less requirement. But over the years, same thing, we've seen a lot of change in the design because it used to be in the past high requirement on pressure, but with a very low flow. So these pumps were rotating at high speed, like 5,000 RPM. Today, there is a requirement on reducing the number of equipment, like gearbox or VFD, and we had to go to a direct drive. So 50 hertz, 3,000 RPM on this pump. And the design challenge was to do the same performance with about less rotational speed. So we have developed our internal hydraulics to match this requirement. And same thing now, in the last generation of PWR, there is a request on cavitation being very high. So same thing, in the future days, I think we'll have to add an inducer on this machine.
Okay, so just following on from what Elise has talked about for emergency cooling on the secondary system, secondary circuit, we have a pump called a TWL. And the TWL started life back in the 1960s and was used as feed water pumps for ships in the shipping industry. And that was mainly because it's a very compact design. It found its way into nuclear power in about 1971. And as you can see, it's again very compact. And I'd just like to spend a bit more time about this pump design. So what is the TWL? What does it actually stand for? Well, it's kind of inherent in actually the design itself. So it stands for turbine water lubricated. It has an extremely small footprint, as you can see from sort of the image here. It's about sort of 1.8 meters long and about sort of a meter wide. So it is, as you can see, compact. The other benefit that we have here is that it's a monoblock construction. So there's no couplings. Unlike other sort of turbine-driven units, which would be a separate turbine and a separate pump with a connection through a coupling, this doesn't have it. It's all integral within this monoblock casing design. And the advantages that gives is that it's basically it's protective for any sort of contaminant entering the pump. So there's no mechanical seals, there's no loop system to this pump, so it makes it a really useful safety critical piece of equipment. So what are really sort of the critical safety features of this machine? I think the main one really is that it only needs steam to operate. And that's what drives the turbine section. And if you come to our stand, we have a very nice model of the TWL, and we can be able to explain its operation in some detail. So as I said, there's no external services because of this sort of monoblock construction, and the only need is actually steam, no mechanical seal, no loop system. So it makes it a very useful sort of pump for safety critical applications. It has a mechanical governor which takes sensing from the pump itself, and then that controls the speed of the turbine. So there's no electrical supply to this, which makes it, again, very, very useful. It also has product lubricated bearings, which are fully integral to the design.
So safety pumps qualification. So one main feature about safety pumps is that versus normal pumps, they will go through a full band of testing to qualify the pump in its accidental condition. So a normal testing for a pump is about 1 or 2 days, sometimes a week. But when we are talking about pumping qualification in safety condition, it lasts about a year. We're talking in years and sometimes 2 years. So you can have 4 ways to qualify your pumps. So it's either by what we call analogy. Analogy, it means that you have a system that is very similar, but it has differences, and you have to justify that these differences will not impact the qualification. So today in the RCCM code, there is a dedicated volume for that, where you can find the type of rules which can apply. Second way, of course, to qualify is analysis, so either by FEA, analytical calculation, so typical calculation. Experience, it means that you have the same product, you have the same component, and you will say the same, I can use it, it's qualified. So this is typically something we do to justify a hydraulic design. And the last one is testing. When you cannot do analogy, you cannot do analysis, then you will do testing. Testing can be either on each component, like a mechanical seal, and it will be done on a dedicated test bed, or it can be done on the full-scale pump. So we will manufacture a full-scale pump with the same material, same dimension, and we will do all the testing for qualification. So on the side, you have here example for what we call standard performance test. But then for that, to do qualification testing, we will have a dedicated test loop. So it is something that is new for pump manufacturer today. They are in charge and responsible for the qualification of their product for these type of requirements. So we had to test our pump for performance, of course, but also endurance. And sometimes it's something like 1,000 hours, even sometimes more. And we had to test it at the normal operating temperature. So we can test it up to 230 degrees C today with water. So it means that the test loop has been designed with a design pressure that is quite high to avoid vaporization in our test bed. We can do also some cavitation test on this test loop, which is quite difficult because the level of cavitation is so low that we are below the atmospheric pressure, and we are below atmospheric pressure. So we had to be careful that there is no air coming inside the test loop, especially when you are at hot temperature. It can be a very significant challenge. We can also do thermal shock because we have to simulate in case of in the power plant, if the source of water is changing, you can have a strong change in temperature going from 20 to something like 200 degrees C. And we had to simulate this through the full-scale pump and having this change of temperature in less than 60 seconds. So when you have, and the flow rate of such type of pump is between 200 and 600 cubics per hour. So it means that you have to design your test loop so that you can comply with these 60 seconds. And also, you need to make sure that the temperature in your test loop will not go way too high. Because if you want to test at 200 degrees and then you end up at 250 or 300 degrees, even temporarily, you will destroy your internal components. So the design of such a test loop requires a lot of calculation and also testing, especially for the thermal shock. We can also do erosion testing on it because we have a requirements on debris going through the pump in case of an accident. And the level of debris can vary between 200 ppm or up to 2,000, 3,000 ppm, which is quite significant. And same thing, we inject the debris in the test loop. We have a dedicated tool for that. But we have to make sure that we don't inject too much, because if we do so, then we have a risk to destroy more our equipment. And we have to make sure that we inject enough to make sure that we comply with the requirements. So it's very difficult to be accurate. So we have designed a specific system so that we know exactly how many grams we are injecting in the test loop. And we measure also how much we have within the test loop constantly to make sure that we always stay above the requirement, but below what could be a problem for the pumps.
So the TWL, obviously being a safety critical piece of equipment, has also gone through some significant qualification testing. So as I kind of outlined, with it being a monoblock construction, it can operate fully submerged, and obviously that's a very important parameter for a safety injection pump. This has been tested within our test facilities. I think there is actually a YouTube link we can give you if you come to our stand, which actually shows this. So it was fully submerged and then operated very successfully. And you know, that's one part of the qualification process. The other part is the seismic qualification process. So the pump was operated. It then goes through full seismic qualification. And then sort of taken off that sort of qualification, and then pump shown to operate after that sort of seismic event. Yeah. Okay, so we spent some time talking about sort of our design and qualification of safety-related equipment, and within Stellaros Flow Technology we have a rich history of manufacturing and designing safety pumps for the nuclear industry, as you can see here. We've basically designed and manufactured 670 safety critical pieces of equipment, and about 45% of those are actually within EDF plants today.
So I will close this session. Just to summarize what we saw today, safety pumps are specific and critical product. This will be safety injection, for instance, will be the first system to start in case of an accident. Today, we need in our facility to have all the expertise to cover many areas of technical expertise. As I mentioned, there is hydraulic, there is mechanics, but there is also vibration, material, all this type, and instrumentation also. And what is the strength today for Stellaros Flow Technology is that we have all this competency in our manufacturing places. In one place, we will have engineering, manufacturing, testing, customer support, so that we can do a direct link between what our customer needs and what we can design. We get the lessons learned from the aftermarket department, and we can adjust directly in manufacturing and testing on our product to give the best answer to our customer. So, thank you.
Yeah, thank you very much for your attention. I think we can take questions. I think we have to take questions into this booth here. Or please come to our stand where we have models of pumps, we have a model of the TWL, and we can answer your questions in more detail at your leisure. So thank you for your attention, and have a good show. Thank you.
Thank you.